Hi everyone, welcome to RPI Data Science. So last time we talked about in the part 6 of our meta-analysis tutorial, and we have mainly talked about the theoretical intuition of the pooling effect size methods and mainly about fixed effect methods. So at the end of my tutorial, actually, I also talked about one example, and we were looking at the depression, and we were pooling effect size using fixed effect size meta-analysis. So if you remember last time, I was mentioning in my also previous videos, somewhere in the beginning of my videos, I was also mentioning the first question before you choose, in continuous outcomes, before you decide which outcome measure, which effect size measure that you have to use, you need to ask whether the scale of measurement is similar. So that means if the scale of measurement is similar, and then you can do mean difference, mainly mean difference. And then after that, the mean difference can be complicated, as I said, because if you have baseline difference and pre-post correlation, you may have to do more sophisticated methods. But for today, I will simply demonstrate simple analysis of final values, which you calculate simply the Y intervention at the follow-up and then the Y, the control group. That's what we actually are going to demonstrate today. We will not talk more on ANCOVA. Maybe in the future, if I have time, I will mainly talk about this. Maybe simple analysis of change score, especially if you have all these baseline values, baseline and follow-up values for both control and experimental group. That's kind of easy to calculate. But for today, I want to show you how to do mean difference from scratch without actually using any package. So we will pull effect sizes from scratch, and I will show you how to do that. So the first thing that we need is data, and then, as I said, we need to assume that because we are going to do mean difference, I'm going to show you mean difference from scratch, not standardized mean difference. So for that, I will have to assume the scale of measurements are similar. So that means so the data we need is like suicide prevention data. I believe the scale of measurements are different, but just for this tutorial purpose, I will just assume the scale of measurements. That means they use the same depression scale. So that means if all of these studies use the same depression scale, so then I can simply use mean difference. If there is one of the studies or some of the studies are different, then if they measure with different scale, that means if one of them is using Hamilton depression scale and the other one using some other depression scale, then you have to use a different effect size measure. That's a standardized mean difference. But for today, just ignore this effect size difference. The effect size measure difference, the scale of the difference in the scale. We'll just assume they measured. It's just for demonstration, so we ignore this scale of measurement difference, and we will simply assume that they were measured in a similar scale, and we will do mean difference from scratch. So for that, I have already loaded the data, and the data looks like this. So you have the orders, and you have the number of sample in the experimental group, and the mean, standard deviation, and then for the control group as well, you have NC, mean C, and then standard deviation of the mean. Then we also have like publication year, age group, and control group in like control. So that means what did the control group get? That means one gets WLC, maybe, I don't know, and then the other one no intervention. Maybe this is usual care or some kind of intervention. But these are studies that we would like to compare and pull together. So as I demonstrated last time, so for mean difference, the mean difference is calculated this way. So you have the mean in the control group minus the mean in the experimental group minus in the control group. So that means you get the mean difference. After that, you need a pooled standard deviation, of course, and then you need the variance. So for the variance, because this is what you need in the inverse variance pooling method, so you need to calculate the variance. So the way you calculate the variance is actually like the standard deviation of the control group squared divided by NC plus the standard deviation of the experimental group squared divided by NE. This is how you calculate the variance. But again, from that variance, because you need to calculate confidence intervals, so for that you need a standard error. The way you calculate the standard error is just the square root of variance. So that's how you calculate it, and this is the way you calculate it. So that means this is just the variance of standard error of the mean difference is the square root of variance of the mean difference. So I quickly converted these equations into functions. For example, for doing standardized pooled standard deviation, I have this equation. So if you remember, the way you do it is we need 4 different parameters. That's n1, n2, s1, s2, and that's all we need. So I already calculated these values, and then the variance is also already there. So the variance, the way we calculate it is like we need 4 parameters, n1, n2, sd1, and sd2, and then the only thing we need to do is we'll square standard deviation 1 squared divided by n1 plus standard deviation 2 squared divided by n2, and then we will return the variance. That will give us the variance. So now what we need is we need to call our data. Our data is suicide prevention data. So the first thing we have to calculate is we need to calculate the mean difference. So I will call that mean difference MD, and then let me just call it MD. And that means that one is calculated by mean experimental group minus simply the mean in the control group. That's how I calculate the mean difference. After that, I think what I need is the variance. I can also calculate the so there seems to be no, this one has to be mean experimental group. So now I will have to now I can also calculate the pooled standard deviation if I want. The way I need it is I will simply call my function that will be pooled standard deviation. Let me just call it pool SD And then after that, I will simply call my function here, pooled standard deviation, and then I will simply call my parameters. My parameters will be like S1. If you remember, the way the order matters, N1, N2, SD1, SD2. So let me just start with the experimental group, and then that will be my N1. The order is very important, not N1 actually, because this is NE, and then the next parameter is N2. So I will simply let me drop it here, and then now the N in control group, and then now what I need is a pooled standard deviation. I mean the standard deviation of the experimental and the control group. So for that, I will call this $sign and SDE. Then I will call again SDC, SDE, SDC. Now my function will be able to calculate my pooled standard deviation if I simply move on this. And now again, for that, for the variance, I will again maybe let me make it larger so you will be able to see it better. And now I already have the pooled standard deviation. The next thing is I need to calculate my variance. So the first variance, I will simply again need N1, N2, SD1, the same parameters. So I will simply call this variance of my mean difference. And then for that I will need actually this variance of mean difference function. But let me just change this value to variance. Now this will be able to calculate. Will help me calculate this. Let me just make it more readable. Yeah, so now suicide prevention variance and the variance mean difference. The variance for the mean difference is I already have a function, so I will have to get that. Could not find function, maybe I made a mistake or I didn't run it. Okay, now let me see if it works. Now it should work, so now I should have values. So if I want, I can also see how actually this suicide prevention data looks like. Now I should have my pooled standard deviation and my variance values. So now I already have my pooled standard deviation and variance. So the pooled standard deviation actually you can also control, because this has to be an average of actually not really an average, but it should be something that lies between the two. So the first one is 3.29 and the other one is 4.41, and then our pooled standard deviation is about 3.9. So it's roughly it's always have to lie something in between, but that depends on the sample size also, because you are kind of using sample size. I mean the sample size in both in the experimental and the control groups. So that's how we calculate the variance. So the next thing you have to calculate is we need to calculate the weight. The weight is usually coming from so now what do we need? So we already have the effect size. That means the mean difference. Oh, I call it DM instead of MG because I need to call it mean difference instead of difference means. It's fine, but we just give it a proper name so I can remember. So and then I will run it, and now so I will have DM. I can remove this one if I want. Let me remove this because I don't need to use my other variable. So for that, let me just remove DM. Now I should find. Okay, remove. Let's contain. Okay, wasn't it DM? Okay, it doesn't matter. So that's fine. I mean, it's okay. We can just keep it. Okay, so now we have the variance. So the next thing is I need to calculate my weight, the weight of each studies. The weight of each studies is calculated by inverse variance, as we have described it last time in our previous tutorial. So we have already put our formula here. So the weight, the contribution of each study is calculated by the inverse variance. So that means we will calculate the inverse of the variance. That means it will give us the weight for each study, and then after that it's simply calculating the mean. So that means instead of the summation of all xi's, that means we will simply multiply the weight by effect size, the mean difference we calculate, and then we will sum these values. The weight total. Yeah, so let me just call that variable the weight. The way I calculate it is I simply let me call it the weight, so suicide prevention weight, and then 1 divided by variance. That will give me the weight of each studies. So we already have the variance, we get it from this inverse variance method, and based on that inverse variance, that will be our weight. If we now run this, we should have the weight at the very end of yeah, so this will be the weight that each study calculates. But if we want to make it in percent, the way you do it is okay, weight in percent, how much one study contributes from the total. So that means that will be the sum. You call the sum. So you divide the contribution of each, the weight of this one, by the total weight. So that means you calculate the sum of the weight. So you do it this way: sum of weight. Now okay, summation of weight percent will be 1 over suicide. So this will be variance divided by the sum. Maybe you can also calculate. Let me calculate it, the weight total. So the weight total would be actually the sum of this, the sum of each, how much of those studies contribute for each. So the summation of each individual study's weight will give us the weight total. So I can simply replace this one with the weight, and then I can see how much the studies contribute. So the weight percent, I have the weight total. I don't need this one to calculate my meta-analysis. I will my pooled effect size measure. I will simply use this one and this one values. But the rest is this is just because you see it in pooled publications. You sometimes see the weight in percentage. That's just for that purpose that I'm bringing it here. Let me run it and show you in percent, and that will be. Oh, okay. I have to multiply it by 100. So that will be 100 times 100 times and then we get the weight in percent. So that means in per 100. So because this depends on sample size, so the bigger the studies with bigger sample size have to carry a bigger weight. So this one contributes only 6%, and this one 1.6, and this one about 25, and this must be kind of large study. So if we scroll up here and see how much the studies, this makes fair. It makes yeah, it makes sense, because this study has 109 in the experimental group and then 111 people in the control group. Relative to the others, this study is bigger, and the other one, this is again is also bigger. So that's why these studies carry bigger weight. For example, this one here, as we have seen. Yeah. Anyway, that's how how the weight is, because it's calculated as inverse variance. It's not only the inverse variance. If you remember the variance, the way we calculated variance is actually this one. It's not only the sample size, but it's also the standard deviation, the variability within the mean will affect the variance. So that will be the way you just take the inverse and then you get the weight. Now the way we calculate, how we already have the weight, we already have the total, we already have the effect size, that means the mean difference here, we already have the mean difference. Now that we would like to pull them. To pull them, as I said, you remember this formula, you have the summation of xi's divided by n, and that means now we have to use, instead of this formula, we have to use the weighted mean, the weighted average. That will be the weight divided by mean difference divided by the total. This is just really an easy thing to do. So the way we do it is, let me just call that pulled effect size, and then the way we do it is like, okay, we sum all the mean differences that we have, and then we multiply that with our weight, the weight of each studies. Mean difference, we have here mean difference times the weight, individual weight actually, and that will be this one here. So we multiply that one with by that value, and then after that we will divide this number by the total weight, by the total amount of, we have, let's say we have 9 studies, and how much weight these 9 studies would be. Now I should be able to get my pooled effect size, that means the pooled mean difference. That's a meta-analyzed value using fixed effect meta-analysis. So now I should be able to get my result. Okay, pooled effect size. Okay, that seems to be wrong, because I would like to get it. That means it's actually dividing it. Okay, seems okay, sum here, sum suicide mean difference. Okay, let me just check this one, and because it has to give me only one value, that's what I need. It's not multiple values. So the pooled effect size should be sum suicide prevention mean difference times, I should not have this bracket, so that would be the summation, and then so I don't need this one again. So that means the sum suicide prevention mean difference times, it's just, if you miss one bracket, then you have a problem. That's why in the weight total, now I should be able to get one effect size measure. So that's my effect size measure, but let me round it. I can also round it maybe in 4 digits, and the way I do it is round into 4 digits. Now I should be able to get this long digit into just 4 digits. There seems to be an error again. Round, okay, this one here. I don't need this R. Now I got the mean difference in the pooled effect size. The next thing is I need to calculate my confidence interval. So to calculate confidence interval, if you remember, the way you calculate your confidence interval is the mean plus or minus 1.96 times standard error. If you know, that's how you calculate. That's the mean x, actually x plus or minus 1.96 times standard error. This is the formula that you calculate the standard error. So that means, let me just do paste command, and then pooled effect size. Maybe let me just ignore this paste command instead, and then maybe let me calculate lower, and the lower bound would be pooled effect size plus the minus, the pooled effect size minus 1.96 times the standard error. And the standard error, we haven't actually calculated standard error, and that will be the way you calculate it. It's like the standard error is the square root of variance. So the square root of variance, that's how you calculate the standard error. We already have the so the way you calculate it actually, so the weight total, this will be 1 over square root of variance, and the variance will be variance equals this one, you take it here, and that's how you get it. So instead of that, okay, sum 1 over var, and the weight total would be, okay, sum 1 var and weight total. Okay, let me just pause for a moment. Yes, so the variance would be, standard error would be the square root of variance, and we already have variance, so that will be here a summation of square root of variance, W total, so that we take the square root of that one, the square root of that value. So that would be our variance. So if you just take this and calculate that one, that would be our variance. This is our variance. Now this doesn't look like, no, this should be 1 over, no, isn't it? Yeah. Yeah, this is our variance. So it's okay. So the weight is like variance is here. So you take this one to 1 over weight, and then yeah, that because you have standard error for each study, so that means you have weight here. So 1 over, and the variance will be here. So you put this weight here. If you replace the equation, if you interchange the equation, the variance will come here and the weight will come here. So that means the variance is a square root of, that means standard error is a square root of weight, square root of the variance. So that means this will go in the square root. So that will be 1 over square root 1 over total. And again, that will be the lower bound. If we want to calculate the upper bound will be simple, just changing it to plus. And now we should be able to get our formula, our pool effect size. And now let me just combine all of them. And maybe I can use paste command and show you how they look like. So first one is the pool effect size, second one is the lower bound, and the third one is the upper bound. So that will be my confidence interval and pool effect size. If I run this, I should be able to get my confidence interval. Yes, I missed one bracket. Now I already have that, but let me again do some rounding. If you want, you can also do it this way, round in 4 digits. It should work like this, but let me check. If it doesn't, we will have to. No, it doesn't work like that. Okay, round, because we have equation here. So let me just pass this with round into 4 digits, and again here again another rounding. So then it will not get a very long boring number. So now I should be able to get my confidence interval, but there seems again another error. So round effect, yeah, this one here. I don't need that one. Pool effect size actually. And this again should be pool effect size, and now I should be. So this is how our effect size looks like, but there should be a comma in between. For that I can also put like a comma like this, and then maybe if you want you can also do like a bracket, maybe 1 comma here and bracket like this, and then at the end I also need another comma. Where is lower? Okay, lower is removed, but let me bring it again. Lower, upper. Something is wrong with my Jupyter notebook, and now I should be able to get all what I need. I simply close the bracket. Now I should be not like this, lower. Yeah, now it should work. So now I have pool effect size, and I put it in a bracket, and I probably need another comma here. Yeah. Okay, but let me do it this way. Okay, now it should work like this. Now if I run it, so this is how it looks like. So I need another comma actually here between the upper and the lower. Maybe I do it this way, and yeah, now it should work. Yeah, now you have the confidence 90. The mean difference is minus 0.3597, and your confidence interval is between 6341 and minus 0.853. But what if we, I mean, we have calculated this fixed effect meta-analysis using our own way. This takes really long steps. You see, as you see, we have to calculate the mean difference, and we have to calculate the pool standard deviation, the variance, the weight. Actually, the pool standard deviation, we didn't use it. The main thing that you need is like you calculate the the mean difference. After that, you need the variance, and then based on the variance, you calculate the weight, inverse variance method, and then you calculate the weight, the mean total. After that, you simply multiply the mean difference by the weight, and then you make the summation. Then you basically get your pool effect size. After that, that's how you calculate the confidence interval. That's what you need. Maybe if you would like, now we already have confidence interval, and you know it's a mean difference, so it doesn't cross 0. So that means it's significant. But because this is mean difference, a continuous outcome, so you need a z-stat. So the z-stat, the way you get the calculate z-stat is the mean difference divided by the standard error. With that, you get the z-stat. The way we calculate the standard error, as I said, is this one, square root of 1 over weight total. So with that, you get the z-stat. So that will be your z-stat. If I run it, that will be my z-stat. And now I should go to z-table and see if the p-value is, where is that p-value. So I can go here, so it's about 2.57. So let me just check, it's 2 minus 2.5, and here is 987. That would be my p-value. This is my approximate p-value. So minus 2.57, it's showing minus 0.508, and then 0.0 p-value of, so we are here, so p-value of 0.0508. So that means it's significant. That's how you get, if you want, to calculate all by hand from scratch. But what if we simply use a meta cont function from the what you call this meta package? Meta cont gives you the first thing you need is you need ME, min E, SDE, NC, min C. The way actually these studies are named are, I mean, the way these variable names are really named is really the way meta cont function needs. So let me just use. Okay, so we also can define data. Let me define the data, and actually I can simply use, okay, the data will be suicide prevention. We already have that, so let me just take that one here, and then after that I can simply define the other ones. So maybe here, first one is NE, NE, total number of people in the experimental group and total number of people in the control group. Now the second one will be the mean in the experimental group and the mean in the control group. Now the next thing I need is the standard deviation of the control group and the standard deviation. Actually, I can keep that one here. Then standard deviation the control group. Now that's this experimental group and the standard deviation of the control group. Now I have to, now once you have all of this, so you have EC, NE, mean C, SD, the next thing is you need to define your effect size measure. So how my effect size measure is mean difference, I will define simply mean difference. If I have to calculate standard mean difference, I have to use SMD, but I'm assuming that the scale of measurements are similar, so I'm using mean difference. Then that will be my effect size measure choice. Now if I run this, I should be able to get these confidence intervals, and let's see if it works well. Now if I run it, I must have some error. Okay, and how that my data looks like? Okay, NE and C, something is wrong here. NE and C, there is no variable time, there is no variable called NEC. Now it should work. So I need to make sure that they are properly arranged in a way. The meta bond function with them, I can actually look how they are, how they have to be. It's really kind of very that's a very long help file. Maybe you can have a look. Anyway, these are meta bond, mean NE, mean E, SD. Actually, NE, mean E, SD. Okay. Okay. Maybe you can put it this way: NE equals NE or NC equals NC. But let me just run it and then check how it works. Okay. Let me see my confidence intervals, and my effect size was minus 0.3597, and then this is how I did it. That doesn't seem to be right. Mean difference 49. Oh, this can't be. No, something's wrong here. This is not right. Or maybe it's calculating the ratio of means. Yeah, okay. Again. Okay. No, it should be variable order should not be like this. So it's like either I have to define NE. This is actually the problem when you don't define your variables. So let me do it this way, because we didn't define our order. So then either I have to define the variable orders according to the way the package is written. Otherwise, I have to mention what the variables are. So because these values, they are written exactly as written in the package. So I have to make sure that they are. So now it should be showing me the right values. Yeah, okay. So that was the problem. So now my effect size is showing me minus 0.53597. This is how we calculated it. And then the confidence interval is also minus 0.63412 to minus 0.853. This is exactly how manually calculated it. So that means our equation here works very well. And the last thing we calculated is the z-stat. Our z-stat is about minus 2.57 approximately. And let's see how the z-stat. Yes, bingo, minus 0.257. And the p-value is about 0.0102. But this is, I think the way we have seen it is here with a, no, this is one-sided. Okay, this is one-sided. So because this is one-sided, so that's why, so minus 2.5, so we have minus 0.0508. If you multiply it by 2, this 5 will be 1, so 116. And let's see how the, yeah, it's roughly like that. So it's okay. So it's roughly approximately our p-value is also approximately 0.01, because this is one-sided. Actually, it's also telling you it's one-sided. To make it two-sided, you have to multiply it by 2. So minus 2.57 was minus 0.0, and then when you multiply it, this will be 10. And this is the p-value that we get it from R. Yeah, well, that's how you calculate fixed effect meta-analysis of mean difference from scratch. So we have seen we calculated the variance and calculate the mean difference. After that, we calculate the weight, and then once we calculate the weight, we were able to calculate the pool effect size and then confidence interval and so on. So that's how we do it. But again, with using this meta-cont function, it's just 4 lines and you have everything. And then if you want the forest plot, you simply pass. Either you save it in an object and pass it with a forest function. There are many other things that you can do after you. With the forest function, I will just simply show you, and that's how this will look like. But let's see how we'll display it in a forest plot. Yes, so that will be how the forest plot displays, and yeah, I think that's all for meta-analysis of mean difference from scratch. Thank you.